All right. Let's go ahead and get started. So just FYI, so today is Mental Health Awareness Day. Where's my pen? There it is. And so not many of us wore green for it. Maybe y'all didn't know. Apparently we were all supposed to wear green.
I intended to do this.
But kind of on the topic of mental health and grades and all that good stuff, so I still haven't made a formal announcement about this, but right now I don't plan on giving any like extra credit assignments. I'm still kind of tossing that idea around. I looked at this class's average compared to my other 104 classes, and it's around the same, so I wouldn't be too worried. You know, there's going to be some curving, but the main thing is get those missing assignments in. So that is what is going to hurt people. So finish anything up. So I've been trying to go through the grade book and update it. I'll kind of continue to do so. I know I'm a little bit behind. But just make sure, even if I've entered a 0 in, you know, you can still make it up, turn it in, just get everything complete. So just try to do that ASAP. Right. Oh yeah, you can close it. Other questions or anything? All right, so let's get through chapter 6 now. So chapter 6 is energy and kinetics, or energy. I started on the wrong page. So energy is anything that has the capacity to do work. So energy can be something an object or a collection of objects possesses. And so work is force acting over a distance. So if you were to, right, if I slide this chair around, so now I'm doing work, and you can calculate, right, what energy I expended. So pushing that chair over a distance. And then heat is the flow of energy caused by a difference in temperature. And so heat and work are kind of the two different ways that an object can exchange heat or energy with other objects. And so we have two types of energy. So kinetic energy is the energy of motion or energy that is being transferred. So you can think of like two billiard balls coming together. So if one comes along, hits the other, right, that energy is transferred, so that movement energy. And then there's also, so thermal energy would also be associated with temperature. So you would have, yeah, the movement of molecules. Oh, I'm so sorry. There we go. Man, you guys were slow to say something. Well, I can tell y'all are paying attention. All right, so then thermal energy is the energy associated with temperature. And so thermal energy is also a form of kinetic energy. So we have our movement of molecules. Of course, they'd be colliding, so they collide again, and that transfers kinetic energy. So then our other type of energy is potential energy. So this is the energy that's going to be stored in an object, and so we'll kind of learn that this is stored in our bonds. And so it can also be due to position. So we're mainly going to be, again, focusing on energy contained in chemical bonds or nuclear reactions. But then we can also have, for example, gravitational potential energy. So you can have, right, your pen sitting in a certain position. We have gravity acting upon it. And of course, as soon as I release it, right, that's transferred to kinetic energy. And so you can see that with that ball here. So again, we go from potential to kinetic energy. And so other forms of energy, and so would be electrical. So electrical would also be considered a type of kinetic energy. So you have the flow of electrons going through your wire. And then heat or thermal energy, again, that's going to be kinetic energy since it's associated with molecular motion. So how fast those particles move, all of that depends on the temperature. And then light or radiant energy, so that's another form of kinetic energy. So we saw that either through, burning it. So we burned our compounds, saw that light. And so again, that's associated with your energy transitions.
Bless you.
Or we also saw it when we passed an electrical current. So again, that kinetic energy in the form of light. And then our two main forms of potential energy that we're going to focus on is we have potential energy when it comes to nuclear chemistry and nuclear reactions. So all those splitting the splitting the nucleus of atoms, that has a lot of energy stored in just those, what would you call it, internuclear forces holding everything together. And so that's very energy dense. Then we'll also look at chemical potential energy. So this would be energy due to the structure of atoms, but of course, right, this is what gives rise to our energy in food, and we can also translate that to caloric energy and all that. So our food gives us energy, and ultimately, that's just due to breaking down and making those bonds. So let's look at our units for energy. So you may have seen this before, if not. So this is just kinetic energy and its relationship with mass and velocity. So for any object, if you do 1/2 mv squared, so that's velocity squared, that is equal to its kinetic energy. And then for our units, so if we have, so our mass is going to be in joules, so that's our standard unit for this. Velocity would be in meters per second. And then so kinetic energy is joules, which translates to kilogram meter squared over second squared. So you can see where that came from that formula, again plugging in all those values. And so 1 joule then is just defined as the amount of energy needed to move a 1 kilogram mass at a speed of 1 meter per second. And then so we have a calorie, and this is not your food calorie yet. So this is just calorie, lowercase cal. And so this is defined as the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And so 1 kilocalorie would, of course, then be the energy needed to raise 1,000 grams of water 1 degree Celsius. And so that means your food calorie, kind of scary thoughts here, a food calorie then is equal to 1,000 calories or 1 kcal. So next time you see that food calorie, you can translate it back. Yeah.
So what you're saying is, chances are, this drink has about enough energy to raise my body temperature to fairly unsafe levels?
Well, you
Considering-
weigh more than 1,000 grams, so we could do the math on it.
Well, has enough to raise it by 160, so at least, not as much,
But I mean, you can kind of get the point that your calories kind of add up. What's more fun to do is to just burn something, and that's a good way of quantifying how much energy. Like if you burn a Dorito, it burns for like long amount of time since it's high caloric, all that fat.
Terrifying.
So other important energy conversions, so then you might want to know, well, what's the relationship between a calorie and a joule? And again, so this is lowercase calorie would be equal to 4.184 joules. So I might jot this down because this will probably come up again. And then we have, of course, our 1 kilocalorie is equal to 1,000 calories. And so we know that 1 food calorie is either 1 kcal or 1,000 calories. And then a kilowatt hour would just be 3.6 times 10 to the 6 joules. And so looking at our first law of thermodynamics, so the first law of thermodynamics is that our total amount of energy in the universe is constant. So we're never destroying energy. So just like matter, right? We saw that in our chemical reactions. Matter is never lost. It's just changed from one form to the other. And so that's the same with our total amount of energy in the universe. So it's constant. And so again, energy is just going to be transformed from potential to kinetic and back and forth. And so we could never design a system that will continue to produce energy without some sort of energy. So maybe you've heard of those like perpetual motion machines. It's just a theory because you can't just have a machine run forever.
There's an easy way to make a perpetual motion machine. Just tie a power source in it.
And that defeats it. So I gotta tickle my nose for some reason. And so looking at now everything at a fundamental level, you know, even thinking of like your broccoli or whatever you ate, or your tea, which is filled with sugar and calories. But what all that fundamentally is breaking and making bonds. And so chemical reactions involve either breaking bonds in our reactant molecule, and then we create new bonds in our product molecule. And so that means that our delta H of our reactions, or delta heat of formation, can be found by comparing the cost of breaking old bonds to basically what we gain from making new ones. And so the amount of energy it takes to break 1 mole of a bond in a compound is called the bond energy. And this is calculated in the gas state and homolytically. And so let's just make sure we know what that term means. And so most bonds are considered homolytic, and that's what you're assuming. And all homolytic means is, let's just say we're looking at this carbon-hydrogen bond. And so all it's saying is for this bond, and I'll redraw carbon's Lewis dot structure. And so carbon, right, contributed 1 bond, or 1 electron. Hydrogen comes, contributes 1 electron. And so when they're calculating this bond energy, when you say you have a homolytic split, all that means, and I'm using these little half arrows to show that these little half arrows kind of mean that you have radical 1 electron movement, because usually you don't have just like 1 electron. When you do, that's considered like radicals. And so in this homolytic bond, you just split that and calculate what energy you would get from doing that. And so if you ever see the term heterolytic, that would be from an uneven split. And again, I just want you to be aware of this. So heterolytic. And so one good example of a heterolytic bond would be this compound. I may have mentioned this compound before. So we have this BF3 ammonia adduct. And so if we recall our 2 structures, boron trifluoride, so boron only has 6 valence, or 3 valence electrons. So it contributes 3, fluorine contributes 1, and so it's satisfied with those 6 total valence electrons. But if we remember, right, nitrogen has that lone pair. And so in this compound, right, what happens is nitrogen comes and ends up contributing both electrons to that bond. So this would not be considered homolytic. So when you split it, you would actually find that the electrons both go back to nitrogen, so leaving you like that. So again, that would be heterolytic bond cleavage, but again, you don't really see it that much. And when you're looking at the chart, just know that it's calculated for homolytic bonds. And of course, the actual bond energy depends on the surrounding atoms and other factors, so how many bonds. And so we can use the average bond energy to estimate, again, our delta H of the reaction. And of course, it also works best when the reactants and products are in the gas state, otherwise it may not be accurate. And so here's the important part. So bond breaking is endothermic. So meaning we have to put energy in. So we have to put energy into the system to break a bond. That kind of makes sense. And so that means that our delta H then would be positive for that part. And then bond making is exothermic, so this would be favorable, and this would be releasing energy back in. So I'll kind of put energy in, get energy out. And so if you take it as a negative value, you can add them together. The other way, I kind of think of it as bonds broken minus bonds formed, since again that bonds form is negative. So whatever you need to do to kind of indicate that you're really kind of subtracting all of the bonds formed. That makes sense. And so these are just general trends. So I wouldn't expect you to know exact numerical answers, but what you can do is you can usually say, well, a triple bond is stronger than a double bond, and that makes sense, right? It's sharing more electrons. Of course, the triple bond is sharing 3 pairs of electrons versus 2 pairs, and we can see that numerically. So 837 versus 611. Again, you would need a chart to reference it, and then a single bond is 347, and then you can compare carbon nitrogen. So again, you see that same trend of triple, double, single, with single being the weakest. And so also, as a general trend, the shorter the bond, the stronger the bond. And so this kind of depends on like their atomic radii and also their electronegativities, so how attracted they are. And so again, you have to compare similar types of bonds, and so we could do this with bromine-bromine versus bromine-chlorine versus bromine-fluorine. And so you can see the bonds get weaker down the column, and that makes sense. So it must just be kind of the physical size which is leading to that trend. And so here's a chart. So again, you would need a chart like this to complete these problems, or on an exam, I would kind of give you, here are the bond strengths of all the ones that you would need, and then you could do these problems. So let's see, what are other strong bonds? So silicon, oxygen, those are strong. Oh, and then just as a note, so if you look at CO, so there's just C double bonded to O, and that's going to be 736. And this will be relevant for most CO compounds, but notice it has a little asterisk here. So when you're computing it for CO2, you actually want to use 799. It has a higher number than just a regular carbonyl. So let's see how this works. We'll do it for this problem. So let's see, we want to look at the enthalpy change for this reaction here. And let's write it out. So we have methane in our gaseous state plus chlorine. Oh, okay. Gives us chloroform plus hydrochloric acid. And so, and it might be better, I should have drawn this out. And so the reason why I'm kind of drawing this out like this is so we can see explicitly what bonds we need to make, what bonds we need to break. And so we're just kind of comparing these two structures for a second. And so I'm kind of noticing, okay, it looks like we're going to have to break this CH bond. And then we're also going to have to break this chlorine-chlorine bond. And then we're going to end up forming a carbon-chlorine bond. The rest of those remain the same. And we'll also form an HCl bond. And so that's our process here. So again, we're going to start here, kind of, this is our enthalpy chart. So this is where our reactants are. We're going to put energy in, right, to break those bonds. So first we're going to calculate what does it take to break this bond, what does it take to break this bond. Then we'll see what bonds we're going to form. So now we'll be getting energy back. So as those bonds form, that's thermodynamically favorable. We'll get that energy back. So we'll see what's that energy in a carbon-chlorine bond and what's that energy in an HCl bond. And then we'll, of course, kind of compare. So let's do that. So let's look at our chart. And so what I like to do is kind of separate them. So I'll do my bonds broken on one side. And so we're going to break one CH bond. And then, so you want to look at, the connectivity. So we just see it's a single bond. So then we go to our carbon hydrogen bond. So it looks like it's 414 kilojoules. And then we look at our chlorine-chlorine bond. So it looks like that's 243 kilojoules per mole. And so just to emphasize things, so this reaction's balanced. We're just breaking one of each of these. So let's go ahead. I'll just total this amount for a second. So it looks, oh, that's not correct. So it looks like we're putting in 657 kilojoules of energy. So let's see how much we're getting back. So now I'll do bonds formed. And so we'll do the same procedure. So we're going to make a carbon-chlorine bond. So I'll go up, try to find my carbon-chlorine on here. So it looks like that's 339. So Again, kilojoules per mole, and then let's see what our HCl bond is. So 431. And we can add this up. So it looks like we'll be getting back 770 kilojoules. And so now we can just subtract them. At least that's how I like thinking about it. You could put a big fat negative sign there too to kind of remind yourself, okay, it's exothermic, so you're getting energy back. But ultimately, we want to do bonds broken minus bonds formed. And so I get that our delta H then of our reaction is equal to negative 113 kilojoules. So again, that's just meaning that we're getting energy out. So this would be an exothermic reaction as we released heat. Again, we can tell that by our negative sign. We can also see that in our chart graphically, how our final products are kind of at a lower enthalpy than our reactants there. So see if you can try this for this next reaction. And I'll let you copy down the reaction and then I'll scroll back up to the table. So we have hydrogen can be made from the reaction of methane gas and steam. So we have methane plus 2 equivalents of water gives us 4 equivalents of H2 plus CO2. So we balanced it for you. So it's important to note all those quantities. And so go ahead and use your bond energies and see if you can calculate the delta H for this reaction. So I'll scroll back up. Let me know if anyone needs to see the problem. Can you see that? Do you mind if I scroll back up?
Did you say that carbon dioxide was different than
Yeah,
So that's just for the bonds of carbon, oxygen, and CO2, right?
yeah, exactly. So just for that scenario.
Edit the energy to break just one bond, right?
Yes.
Okay.
Yeah.
You have to like picture how they would bond, like if they were two similar metals.
Yeah, so you have to figure that out. So let's kind of see what we have so far. So yeah, the first thing, that's the problem with chemistry, it's just cumulative by nature. So you kind of have to draw your Lewis structures first, so I would just do that. And it may help to draw it all out. So I'm going to draw like 2 water molecules just so we can really see it. Put my lone pairs on oxygen. So then hydrogen, make 4 of them. So I'm just, again, just being really explicit. And then CO2. So yes, it was a little tricky one. So you had to know kind of what it looked like. Although the chart did help. But so then what bonds do we need to break?
We need to separate the hydrogen-carbon bonds. Carbon.
Gotta break all these.
Just be carbon tetrahydride or just be carbon hydride?
What, how to name this compound?
Yeah.
I guess it would be carbon tetrahydride, but it's just methane.
Oh,
It's so
methane,
common,
duh.
yeah.
Methane. Sorry, brain fart.
So then what else do we need to break? We gotta break all these too, right?
Is that 4 bonds total then? For that one?
Yeah, I guess for oxygen, hydrogen, if you wanna look at it that way. And so now we can start putting some numbers to this. I see it in the chat too. Thanks for checking in. So chat agrees. We got to take off all these hydrogens on everybody. So I'm just going to start with CH.
Okay, so it's
So times 4. So what's our carbon hydrogen strength? Y'all can shout the numbers at me.
414.
So 414, so times 4, so we'll have to add that up. And then do we have a OH bond? Do you have a number?
Oh, yeah, 464 for the OH bond, but we have 4 of them, so 1,856.
So do you have a grand total of what we have to put in?
Oh, yeah, for the total amount of energy we need to put in, 3,512.
Is that what other people got?
Yeah.
Excellent.
The amount of energy out, oh, we're not there yet.
So now that spawn's broken, I'll kind of put my line over here, or broken. So let's see how much energy we'll get back in our bonds formed. And so now we have to make 4 HH bonds. Do we have a,
1,700, so, yeah,
Is that
1,744.
for all the 4 H's? So 1,000,
436 is each individual. No, 1,744.
744. So that's for our hydrogens. That's not the color I wanted. And then, so the CO, y'all caught on pretty quickly that this was that special case of the 799 for CO2. So what's 799 times 2? $1,598. So what's our grand total for energy that we get back? What'd you get?
3,342.
So is that what you got as well?
No. But I didn't have the CO2
No, did other people get 3342? I just want to make sure we're all on the same page and no one did a calculator error. So 3342, I see in the chat, so it looks like chat got this. And so now we'll figure out how much energy we either put in or gain back total, so our delta H of our reaction. So I'll do 312 minus our bonds form. And so I get a positive delta H of 170 kilojoules. And so that just means that our reaction would be endothermic, meaning we'd have to put energy into it to get that reaction to go. Any questions on how to do those? So let's look at kind of the rest of the chapter. So like we've been looking at, we can distinguish between these exothermic and endothermic reactions, and then we also have these energy diagrams as just a graphical way of showing which way the energy is flowing. So in this one, if we're comparing, so again, this is energy on our axis here. We have our reactants are starting at a higher energy. Did you have a question? It's something you can get online. I could make a copy of it. It's just usually for exams what I do is I just give you like the few ones that you need. But yeah, it's readily available online. It should be in your textbook as well, but I can print one out for the future. But if we look at this reaction diagram, so we notice our reactants are higher than our products. And so that means that this reaction would be exothermic. So that energy difference here is what's lost as heat in this case. And so again, we see our CO2 products are lower in energy. And so that also means if the reactants have a lower internal energy than the products, the change in energy will be positive. So if we look at our system to our surroundings, so if our system is negative, then that means the surroundings have to have a positive energy, right? So the energy has to go somewhere. And so that means for these exothermic reactions, they're going to feel hot. So you'll feel that energy that's being lost, and they'll be given off as heat. And so you can think of like those little hand warmers. So I think those are just like some sort of iron powder, and then those react with the air, and of course make your hands nice and warm. And so this is just another way of showing really the same thing. So we can see, right, our reactants, our products. But instead what we've added in here is now we're showing this transition state. And so that would be, kind of think of it, right, as that middle state where everything's kind of in flux. So if we were looking back at, let's just say this reaction, so that transition state would be, again, high in energy. And so let's go back to this. So that would be where our methane, so we'd have our methane, 4 bonds, and then it's like almost forming this chlorine bond, and you could kind of draw like a dot to one of the hydrogens. So we're about to make a bond, we're about to break a bond. So that would be our transition state. And so of course this transition state is also fleeting and does not last very long, but it's also higher in energy. And so notice you also have this energy from your reactants to your transition state. And so this is our activation energy. So you can see that abbreviated EA. So activation energy. And I always think of that as, the energy that it takes to get you out of bed. So you're in bed, you're the reactants, and then finally, it takes a lot to get you up and going, but once you're up and going for the day, usually goes.
It doesn't take much for you to go back to bed.
It all goes downhill.
Very unstable products.
It sounds like a lot of us end back in bed, so you need a lot of coffee, so maybe you have a very high activation energy, Red Bull, or I don't know what substances y'all abuse these days. So, and again, the main point for, and this is an exothermic one that we're looking at still. So exothermic, again, you can identify that our products are lower than your reactants. And so this energy difference here from our reactants to our products would be equal to that delta H that you calculated. And so for an endothermic, that graph is obviously just going to be a little bit in reverse. So if we were to take this process of CO2 and split it back into solid carbon and oxygen, so first of all, it doesn't look like that would be the most favorable reactant or reaction, since we have our products at a higher internal energy, so we have to put energy into this system to make that happen. And so again, if now our system is getting energy, that energy had to come from somewhere, aka our surroundings. So our surroundings will be negative, and that's why these endothermic reactions would feel cold, since your body is supplying that energy needed. And so I believe, like those cold packs, if I remember correctly, I think they're ammonium chloride salts. So usually it's like ammonium chloride and water, and then you kind of break that metal seal. And that dissolution process is endothermic. And so again, your body is kind of supplying the heat needed to dissolve the ammonium chloride, but then it, feels nice and cold for your little ice pack. And so here's our now full energy diagram for an endothermic reaction. This endothermic, so it's clear. And so once again, right, we have this transition state. So we have a high activation energy from our reactants to our transition state. And then, of course, our products, again, would be higher for an endothermic reaction. And so from here to here, that's going to be your activation energy, as indicated by that red line. I just want to make that clear. And then our difference in energy from our products to our reactants is going to be that delta H, again, just like you calculate with your bond breaking, bond making. So now let's look at chemical kinetics. So chemical kinetics is just referred to the speed of the reaction. And so kinetics is also something that you have to kind of measure. So if you're doing a reaction, you have to have some sort of monitoring to see how fast it's going. So this could be done by a lot of different techniques, so it depends on what your products are. But commonly they just use like spectroscopy. So that could be like UV vis, like we might do in class. You could also use different NMR techniques or do sampling, mass spec. But anyways, you have to have some way of quantifying, right, how fast you're consuming or making products. So either you're measuring your reactants and how they're disappearing, or measuring your product formation, or maybe both. And so the ability to control the speed of a chemical reaction is important. So of course it's most important in industry or something where you want to know the rate at which chemicals are formed and how to make it safely. But the other thing is, safety of a reaction. So you could add something that's too exothermic and then things go boom. And so you want to be able to slow that reaction down if you need. And so the main things, we'll look at kind of the main things that affect reaction rate. So the big one is reactant concentration. I think you'll do a lab which shows that. But generally, the greater the concentration of reactant molecules, the faster the reaction. And that makes sense. So, right, molecules have to collide and see each other for a reaction to occur. So if you have more molecules in the same space, then that means they're going to collide more frequently. And so the same thing would apply to gases. So if you have a higher concentration, aka higher pressure of gases, then that's going to lead to faster reactions as well. And then so you would see that in solutions. So that would depend again how concentrated your solution is. And it's measured in molarity, which we haven't gotten to, but I'll just define it for you as moles per liter. So basically, right, how many things, what's our quantity in our set amount of liters. And of course, you can see that. So as you might imagine, temperature also affects your reaction rate. And so this is just kind of a fun fact. In general, for every 10 degrees Celsius rise in temperature, the speed of the reaction doubles. And of course, this would be, within limitations. So every chemical has different melting points and then eventually a decomposition point. So you can't go too crazy. And so we'll look at, this will be more for our gas chapter, this relationship between absolute temperature and speed. That's section 6. So I was checking. So I think my next page is this one. So now let's kind of look at equilibrium. I know we're like flying through a lot of concepts, but so if we look at how oxygen is transported, so this is all chemical equilibrium. So you have this hemoglobin protein. So what happens is, of course, when your hemoglobin goes to your lungs, it's probably oxygen deprived since it just came from your muscles. And so at this place, again in your lungs, it has a high concentration of oxygen. The hemoglobin doesn't have anything because it should have just deposited oxygen. And so that means, again, in your lungs, this would be favorable. So then we make our hemoglobin bound to our oxygen. And then so this travels around, right, to your toes. And so once it gets to your toes or wherever it needs to go, now our equilibrium is different. So we would not have a lot of oxygen, right, because your muscles used it up running or walking. And so in your toes and your muscles, it would be favorable for this hemoglobin and oxygen to disassociate. So of course, leaves that oxygen behind for your muscles and everything to use, while that hemoglobin travels back now to the lungs to get a new oxygen molecule. And so notice too, we have this new type of arrow. So we have our equilibrium arrow. So previously, right, we had just been looking at this kind of single arrow, which just kind of indicates that our reactants go to our products and there's no reversibility. But now that we have this equilibrium arrow, that also indicates that our reaction can kind of go forwards and backwards depending on the condition. And so just so there's no confusion, don't confuse it with our resonance arrow. So remember, that's just for movement of electrons, such as in benzene. So again, you're not changing anything, we're not showing any reaction, we're just showing electrons moving around. So that's our double-headed resonance arrow versus our right two half arrows for equilibrium. And so we can quantify then everything by this equilibrium constant K. And so we put either like solutions in here for our equilibrium expression. So this is appropriate for solution concentrations, as in molarity, or it could also be used with pressures or gases. It would have the same sort of form. But all this is, so let's say we have this generic reaction. So we have our reactant A, and this would be, right, its coefficient here in our balanced equation, plus reactant B, and again, our coefficient from our balanced equation, gives us product C, and C is our coefficient, plus product D, with D being our coefficient for a balanced reaction. And so once we have that, all we have to do is remember that it's products over reactants, and then you just need to take everything to the power of its coefficient in our balanced reaction. So you see that our K expression is equal to, so our product to the power of C times D to the power of D over our reactant A to the power of whatever that coefficient is times B to the power of our coefficient. So star that, whatever you need to do, note that it's important. And so this is just our equilibrium constant, and it should be unitless since everything will be canceled out. I didn't want to reveal the answer. So take a minute or so. So can you write then the equilibrium expression for K with this reaction? And it is balanced for you. So the uppercase just meant like whatever your product is, like A. So this would be A, and this would be little a, right? And so this is B, little b. Of course, now I screwed it up because you use C. C, little c, D, little d.
Alright, so what number would you put in for capital A?
So you would have to be like a molarity. So we would just, so let's go over kind of the answer. So all this signifies is concentration. So we could write this expression. So I don't know if you got this or if everyone got this. So we got products, right? So we have our NO2 to the power of 4 times our oxygen concentration to the power of 1 over our products, so squared. And then so you would have to have like a problem that says, you know, like, and we probably will get there. Well, eventually we'll get there, but I'll just give you an example. So if we were to say like at equilibrium, the NO2 concentration is 0.113 molarity, you know, O2 is 0.05 molarity, and N2O5 is 1.1 molarity. So you would have to have something like that, or it also works for pressures, or at least it's very similar. There's a relationship to go from solutions to pressures, but all you really need to know is you'd be plugging in like an ATM, so like, oh, 0.97 ATM, that sort of thing. I just made up numbers. So are we all okay with at least writing just kind of the basic expression for this? Again, understanding that we'd have to plug in like a concentration or something here once we actually get to the calculating part. Are you referring to this thing? Yeah, so copy that down, because that's really important. So do we all have this copy? And then, so now, this can tell us kind of which way our equilibrium lies. So now the first part, and this is just for, you know, thought exercise. So when the value of K is greater than 1, when the reaction reaches equilibrium, this means that there will be more product molecules than reactants. And again, just take it back to your general expression of products over reactants. And so we know if it favors the products, right, it starts approaching kind of infinity to 1 type of thing, or really greater than 1. And all we need to know is if it's greater than 1, favors the products. And so in this expression, so you might calculate a K value of 1.9 times 10 to the 19th, so that's pretty large, and so that's telling you, right, the equilibrium lies pretty far to the right then with our products. If it's less than 1, so again, think back, okay, products over reactants, it's starting to get less than 1, so I start thinking about, okay, 1 over now an infinitely large number, And so that's telling us that it's favoring the reactants then. And so for this reaction, so this is the reaction of nitrogen plus oxygen to give us 2 equivalents of nitrogen monoxide. So if you were to calculate the equilibrium for that, you would get a K value of 4.1 times 10 to the negative 31. And that makes sense, right? Because if this was a really favorable reaction, we probably wouldn't have a lot of oxygen to breathe. So, and so it would all be NO. And then,
Oh.
sorry. And then, so if we have K is equal to 1, all that was saying is that our reactant and product concentration are about the same. And so now from this, we can look at Le Chatelier's principle, which is now going to tell us how we can kind of influence the reaction and push it. And so once a reaction is at equilibrium, the concentrations of all the reactants and products remain the same. That's all that's saying. And kind of the way to think about it, too, let's just look at this reaction of our nitrogen plus oxygen gives us NO. So at equilibrium, right, there's still reactions occurring. So if we're looking at the molecular level at equilibrium, there's still a lot of action going on. So right, there's still bonds being broken and bonds being formed. But then overall, nothing is changing, right? So however much you make, and it reforms your product and kind of back and forth. But then, if we change the conditions, so we could perturb them, and then all of our concentrations will change until equilibrium is restored. And so we'll kind of see how to manipulate that. And of course, our new concentrations will then be different from our original equilibrium, but the equilibrium constant will be the same unless you change the temperature. And so Le Chatelier's principle just kind of helps us predict the effects of various changes, and again, maybe how we can kind of optimize a reaction for certain conditions. And so it says that if a system in equilibrium is disturbed, the position of the equilibrium will shift to minimize the disturbance. And so disturbances, of course, involve making the system open, aka meaning we're like adding stuff or we're taking stuff away. And so let's look at this. And let's just look at, we'll stick to this nitrogen-oxygen reaction. So there's something to look at. And so, again, it's at equilibrium. Let's just assume that. And so, after equilibrium is established and a reactant is added, then of course it's going to influence it as long as that reactant is included in the equilibrium constant expression. And so all this is saying is, okay, these are in the gas phases. Let's say we were looking at another reaction of carbon solid plus oxygen to give us CO2, so oxygen in the gas phase, CO2 in the gas phase. So we could add as much carbon as we want, but this is not going to influence your rate of the reaction. And that's because it's a solid, so it's not included in our expression. And it would just be, right, one pile of solid anyways, kind of limited by your surface reactions. So again, you could put in all the solid carbon you want. That's not going to change it.
What if it's a really, really fine powder?
Still won't change it. And so same thing for liquid. So if you're doing it, you know, sometimes it's called like a neat reaction, which means no solvent. And so, of course, changing that concentration of whatever that reaction, so you can do a neat reaction if like your reagent is liquid, but if you add more of that liquid reagent, it's not going to do anything. And so let's see what will happen. And so we go back to this N2 plus O2 reaction. So even though this isn't really favorable, we could put a bunch of nitrogen into our system, right? So now we're flooding it with nitrogen. And so if we add a reactant, this would initially increase, right, the rate of the forward reactions. Now we have a bunch of more more reactant. So that's going to cause it to react with more oxygen and form more of our products. And of course that will continue until equilibrium is restored. All right, so it's going to be favorable. And again, you can tell it's going to be pushed to the right since you're adding reactants. Does that make sense? And so how will it affect the reverse reaction? So at our new equilibrium position, so this is kind of after the fact, we'll have more of our product, right, since more of that N2 made more NO. And then we would have less of the non-added reactants. All that's saying is, okay, we would consume some of that O2 to react with our excess nitrogen. And of course, we'd have less of that added reactant that again pushed the equilibrium to the right. But it says, but you will not have as little of the added reactant as you had before the addition. AKA, you're going to have, more than whatever that first baseline equilibrium was. And so how does it affect K? So it does not. So once it establishes our new equilibrium position, that equilibrium constant is the same. So that's really key, especially in the math of helping us figure out things, is we can always go back to our K and then figure out what our equilibrium concentrations will be. And so if we remove reactants, then that would cause our reaction to shift and make more reactants. So again, if we're looking at this scenario, let's say we take out N2 from the system. And again, it has to be something that is in our equilibrium expression. So we remove N2. So now that's going to drive the formation of this NO to split back into its components of N2 and oxygen. And so we can see, so how does this affect the rate of the forward reaction? So if we're removing reactants, so of course that would decrease the rate of the forward reaction. And then no initial effect on the rate of the reverse reaction, but of course if it's decreasing the rate of the forward, that means it's going faster in reverse, and it will proceed to the left, again forming more reactants until our equilibrium is disturbed or restored. And so once again, right, our K will be the same. Let's look at that, kind of this graphical representation here of what it's saying. So now we're looking at this dimerization reaction. So this is dinitrogen tetraoxide plus nitrogen dioxide, or forming two equivalents of nitrogen dioxide, and then this can go back and form our dimer here. And so we can kind of see graphically what all this was saying. So if we look at it graphically, so we have our system at equilibrium. So we have our NO2 concentration and our equilibrium, right, dinitrogen tetraoxide. And then of course we disturb the equilibrium by adding more of, in this case, our product. And so if we add more product, that's going to drive it to the left. And so we can see that right now we're forming more N2O4 right as we add more NO2. And of course, this will decrease until it reaches its new equilibrium value. And same thing with N2O4. So now it's going to increase right until we're back at equilibrium. And so kind of looking at the reverse of this, so now if we add a product in the form of N2O4, so again, we disturbed our equilibrium, and so that means now we're going to start generating more NO2 as it drives a reaction to the right, and then equilibrium is, of course, reestablished. And so this is also like a really good way to drive condensation reactions. This is another aside. But in these condensation reactions, you're adding two things together. So like molecule A plus molecule B, and it gives you one product C, but then you lose water in the reaction. And so if you want to drive these reactions forward, there's actually a special apparatus. Oh, I mean, I guess you could. So there's a apparatus called a Dean-Stark apparatus, and so it's this little thing on the side here. So you would have your reaction. Here's the little adapter and a little reflux condenser. And so what happens is you start boiling your reaction, and let's just say, you're using like toluene or some organic solvent. So that's boiling, and then the vapors are going to go up here. And so this is a water jacket condenser. So eventually it's going to hit up here, our vapors. They're going to condense and cool down. And then in this Dean-Stark collection flask, you'll get a mixture of water and toluene. But what's going to happen is water, and you should pick a solvent that water is more dense than, so that it's on bottom, because there's a few organic solvents that are more dense than water, so that would...
Lighter than water?
No, I mean, you would want to pick a solvent lighter than water, but there are some organic solvents that are heavier. There are very few.
Sorry.
But like DCM, for example. DCM is heavier than water, so that would not work. So you need water to be on bottom, and so your water collects, and then you see this little stopcock here, and let's say your reaction's really making a bunch of water, or you're doing a large scale, you just drain the water out to the bottom, your toluene or whatever organic solvent collects on top, and then eventually makes its way back to the flask. And so that's a really great way to drive reaction forwards. So here's just an example setup. So you can see that person's flask, there's their Dean-Stark, and then their reflux condenser. And so that will, again, drive that reaction forward. You'd also want to think about, like if you were in industry, you'd want to think about how can you drive your reaction, how can you keep removing your product as it's formed to keep, your reaction moving forward without wasting energy. So let's see, we only have a few minutes. Just trying to check. All right, this is our last page of the chapter. So the last thing to talk about are catalysts. And so catalysts are generally substances that affect the rate of the reaction without being consumed. Usually they're used to speed up a reaction, but I will say that there are some catalysts that impede a reaction. I was wondering if I had it
Are
on.
they called inhibitors or something? Or
They
still called
are.
catalysts?
So you're right in they're called inhibitors, so I would use that term, inhibitors.
Oh, inhibitor is that an accelerator.
Yeah, so this would slow the reaction, but I think sometimes people just call them like negative catalysts, and there might be other terms for it. But again, usually you're not interested in inhibiting a reaction, so usually you're trying to make it go forward. At least that's what most of what chemical catalysts do, or help reactions, not impede them. But how they work is they provide an alternate mechanism for the reaction with a lower activation energy. So that's just meaning it's creating like a whole different pathway. And so you can just kind of see this is a nice simplified mechanism. So we have ozone plus oxygen radical gives us two equivalents of oxygen. And so this is slow, but with the catalyst,
Very slow. There's that.
yeah, very slow. And so this would be like radical atmospheric chemistry, and this is why people get, worried about volatile chlorinated substances, because you could have this reaction now where you have a chlorine radical plus our ozone. So then it would make oxygen plus the ClO, and that's fast. And then the ClO would go on to react with another equivalent of oxygen radical to give you your second equivalent of oxygen plus chlorine now, or chlorine radical, I should say. And so again, that's a completely different pathway. And so looking at our energy diagram, so this is a good representation of what's going on. So our blue line is our uncatalyzed pathway. And so again, if it's uncatalyzed, that usually means it's higher in energy. And then with this catalyzed pathway, since it's going through a different reaction mechanism, then it has this lower activation energy. But then, of course, we have kind of these two steps. In this case, it's going through kind of two smaller steps with smaller activation energy. And I wanted to pull up just a picture of this is probably not the best picture. Let me find another one while I look at this. So this is an example of a catalyst. And so this is really famous, these Grubb catalysts. So they're good for olefin metathesis. They really changed the industry. But you can see that they have, this metal, and they provide a whole new pathway since our substituents can bind to the metal, and then it would undergo a transformation. Metathesis.
Metathesis?
Yeah.
Again? Sorry.
It's a reaction type olefin metathesis. And so here's just another kind of representation. So there's your metal with, and this is olefin metathesis. So basically you're just kind of swapping substituents. But it allows you to do that since our reactants can bind to this product or to this catalyst. So you can see this in this mechanism better. So it binds, makes these bonds, and then it can do these different metallation reactions and does this little bond swapping, all because of the metal. So that's pretty cool, just again that it's going through different pathways. All right, I think that is it, since we're out of time, and I think we're out of the chapter. So let me know if there are any questions or anything. So I have the homework for this week for people to grab a copy. And then, like I said, just keep up with the assignments, finish anything that's missing, because I don't want missing assignments to be what hurts y'all. So just get that turned in and let me know if you need help. And of course, we can meet in person or by Zoom, either way. So thanks again. I'll hang around on stream. Otherwise, have a good night. Thank you. I'll take homeworks if people have whatever.
Are you still waiting for the documents?
Uh,
They all be in there.
like physical homeworks
Yeah,
or?
physical.
most of the physical homework should be graded. I think I'm behind on labs. If you're missing something, just email me.
Email you all.
Yeah, and I do have like a homeless homework, but I don't think I brought it to class today.
Oh, I have like chapter 4 and chapter 5 that are not graded yet on my
I-
Blackboard.
Wasn't it like
Oh,
a
if it's
chapter
through
3 or
Blackboard, I
something?
haven't
Oh,
done it. I'm almost there. But yeah, if you physically handed me something and it's not there, definitely email me.
no, it was, I physically handed it to you, but the grade's not in Blackboard is what I mean.
Okay, then, yeah, then email me. Other questions on the stream, or else I'm gonna shut the stream down for you. Thanks.
I'm just saying that things have rated.
All right, thanks again, chat. I'm gonna end the stream.